I forgot to press the button, doesn't matter. Should be fine. I'm gonna start again with the short definition or method or the idea behind the method. And then we're basically gonna keep on doing exercises for probably an hour and something. And maybe in the last 30 minutes, I will show you the last method, which is just the substitution, which I think is the trickiest out of them all. But let's see. So I did say last time, and I started by saying that the integration by parts comes from the product rule, right? If I was taking a derivative, f of x times g of x, derivative of x, this was just f prime x times g of x plus f of x times g prime of x. This is just the product rule from differentiating. And now if I integrate both parts, so I'm going to integrate here and here, I can just write everything as integral derivative f of x times g of x dx. Oh, there's no need for parentheses. You know, I have to put a dx here just to show what I'm integrating from, and this is equal to integral f prime of x g of x dx plus integral f of x g prime of x dx. I basically just split the two. And this, remember when I argued that differentiating is the opposite of integrating, or integrating is the opposite of differentiating. So I have integral of a derivative. So this is just equal to f of x times g of x, okay, is equal to this thing. And now the whole procedure that we're going to try to do, the whole idea with integration by parts, is we are going to try to write our integral in some shape like this. That's our whole idea. And I'm going to show you how now. First of all, whenever you see functions of the type e(ax) times x to the power of n, or x to the power of n times an ln of x. Whenever you see something that looks like this, and you have to compute integral of something that looks like this, you should always think by parts, because it just works out very, very nicely. They're like standard applications. Let's see if I have an example that's not complicated to start with. I think I kept one example. Yeah, this is fine. Okay. So, for example, I want to compute integral x squared ln of 4x dx. I just want to compute this integral. You can stare at it for a while, but it doesn't have the, the nice polynomial formula that we're used to, right? That we did last time. Last time we did all sorts of integral from x squared plus 3x to the 4th plus 5, etc., etc. This one looks different. It looks much uglier, right? So now the whole idea is to come back to our formula. And I did say, and I argued that we are just going to try to write our integral in some shape like this. That is what I'm going to be aiming to do. So if you look at this, I'm just going to say, I looked at it for a while, and what's the idea? I need to have some f of x and some g prime of x, okay? So I need to have an f of x that I'm going to take a derivative to get this f prime, and a g of x that I'm going to integrate to get that gx. Now, listen from me. You never want to integrate ln of 4x in a by parts. You never want to do that. So I'm just going to say this x squared is my f prime of x, and this ln of 4x is my g of x. Okay, so I'm basically just choosing at this point. The other choice that I could have made was, so, let's write it out. So my first choice is f prime of x is equal to x squared, and g of x is equal to ln of 4x. That's my first choice. But I could also do it the other way around. F of x is equal to x squared, and g prime of x is equal to ln of 4x. Fair? Because I have two integrals right here. I have two integral signs. And in the first one, the first f of x is derivative, and the second one, g of x is derivative. So I'm just choosing right now which of these integrals is my integral that I have to solve going to be equal to. And I have these two choices. I either have the first one derivative, or I have the second one derivative. The idea that follows now is I have to compute from here f of x. So basically just compute integral of x squared dx, or you can just, usually they're going to be pretty simple, so you could just say, what if I take a derivative of, do I get x squared? And the answer is x to the third over 3. No constant. I don't need to put constant here. And since I have g of x here, I need to compute g prime of x, which again, I'm pretty lucky because ln of 4x is derivative nice is 1 4x times 4. I think so. Oh yeah, I don't know why I wondered for so long. Yeah, okay. Now, let's see what would happen if I picked the other one. If I picked the other one, so this one looks pretty nice. I can compute everything, and it works fine. The problem is that if I do the other one, then I have to compute f prime of x, which is fine. This is 2x. This is nice. But the problem is here, because I have to compute g of x. So I have to compute integral ln of 4x dx, which I would highly advise you never to do in doing by parts. Okay? So this is bad. This is bad and it's ugly, and you're going to probably end up with something uglier than you started with. Okay? So always take this route when you're dealing with x to the power times ln. Okay? Now, let's see actually what we get. So, I'm going to try to write it slowly. I promise I'll give you 1 minute to write afterwards, so just follow what I'm doing, okay? I would suggest for the first time not writing. So, my formula is, I'm going to copy again the formula. My formula is f prime of x times g of x dx plus integral f of x g prime of x dx is equal to f of x g of x. This is the by parts. And now I'm going to slowly replace what I know. So I said f prime of x is this x squared. So I have integral of x squared times ln of 4x dx. Basically just copied it. And now I'm going to replace the parts that I'm missing. So f of x is x to the power of 3 over 3. So integral x to the power of 3 over 3 times, what is g prime of x? G prime of x is 1 over x. Dx is equal to, what is f of x? F of x is x to the power of 3 over 3 times ln of 4x. All right. Now, what was the idea of writing it like this? Well, let's analyze. Let's look for a second. The idea is, this is what I had in the start. I need to compute or whatever to find out what it is. The trick is that here on the right-hand side, there's no integral sign. No integral sign. No sign. Since there's no integral sign, it means it's done. There's nothing I need to do to it anymore. So it's done. And the only thing I have left to compute is this thing. But you can see that it has actually a very nice form, right? It's just x squared and a constant. So it's just I have left to compute. Okay, and basically this is all the by parts that you're gonna see. Obviously, maybe a little bit more complicated format, but this is the essence. So again, let's go through what I did. So I was given this thing to compute, this integral, which I have no idea what it is. And the standard approach with splitting the integral and you looking at polynomials or see if I can guess the function doesn't work unless you have a lot of experience. There's no way you can in which you're going to tell me this is equal to blah 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 blah. So you need to work it out. And the only method that works here 100% is the by parts. It's a standard form. It's one of these forms. So it should automatically be imprinted in your heads that I see this, I need to apply by parts some way. Okay. The next step is to see how I'm going to apply by parts. What is my f prime and what is my g prime? Okay. And I gave you the two options. These are the only two options in which you can apply by parts. You either take the first one as being derivative or you take the second one as being derivative. And I wrote it right here. First one derivative or second one derivative. Then you need to compute the opposite. So for example, if I say this is f prime, I have to compute f. If I say this is g, I got to compute g prime. So I need to compute the other remaining terms. And in the first case, I got some nice formulas that worked out. In the second one, you had to compute integral of ln of 4x, which I told you not to do, okay? Unless you are 100% sure that it doesn't work the other way around, this is bad in 99.9% of the cases, okay? Once I've computed my terms, so I have f prime, f of x, g of x, and g prime. Once I have these four terms, I go to my formula. And now, hopefully you understand why I need all four of them, because I see all four of the terms. I see f prime, I see f, I see g prime, I see g. So I need all of them. And now I'm just going to plug them in. So I plug them in, and I see that the first term is the thing I needed to compute originally, and that's no mistake. That's how I created it, right? The second term I have left to compute. I don't know what it is until now. But the idea is that the last term, there's no integration sign, so it's done. There's nothing I need to do to it anymore. My last step to finish the problem is just going to be, I'm just going to move this thing to the other side. So I'm just going to move it here on the other side. And I get integral of x squared times ln 4x dx, which is what I had originally to compute, is equal to x the third over 3 ln of 4x minus integral x the third over 3 1 over x dx. Now let's see what we can do here. So x goes away with x third and I get x squared. And now I can see why this by parts is so strong, because what do I have here? I just have integral of x squared, which we solved last time, several times. So my final answer is just integral x squared ln of 4x dx is equal to x to the power of 3 over 3 ln of 4x minus, this is just integral of x squared, so it's just x, a third in front, x the third over 3 plus a constant. Always put a constant since I have no limits of integration. And this is it. I've successfully used by parts. Any questions on what I did? Okay. Now let's do the other most common example. which is, do I even have an example for that? I think I should. That's ugly. Let's do that. Yeah, let's do another simple one. Integral of x e to the minus 6x. Yeah, that's fine. That's fine. Dx. Okay. I'm gonna proceed exactly the same way. Let's just do plus. I don't want you guys to focus on the signs and lose track of exactly what we're doing. Okay. So now again, first step is trying to see what my f and my g of x are and what the derivatives are. So the question that I have for you guys is, what is easier to solve? Eventually, so for these basic ones that look like this, like these two cases, you don't really need to overthink it because they all solve the same way. But at some point, you should be asking yourself, is it faster if I do it this way or that way? In this particular case, is it faster if I say f prime of x is equal to x and g of x is equal to e to the 6x? Or is it faster if I say f of x is equal to x and g prime of x is equal to e6x? Okay. These are the only two cases. I'm identifying again my f and g, and I'm seeing which one is prime, which one is not prime. These are the two cases, right? So let's see. If f prime of x is equal to x, then f of x is x squared over 2. If g of x is e to the 6x, then g prime of x is equal to 6 e to the power of 6x. That is the power of the exponential of x. Whenever you take a derivative or you integrate it, you're just going to get a constant next to it, which makes it very nice to work with. And whenever you have exponential integral of something exponential, it's a prime example of using by parts. It's going to work probably 95% of the time. Now, if f of x is equal to x, then f prime of x is equal to 1. And then if g prime of x is equal to e6x, g of x is equal to e6x over 6. Okay. Now the question comes, what is easier to work with? What do you guys think is going to be easier for me to solve? Case 1 or case 2? Just by looking at it. You don't have to really imagine how to solve it in your heads. Just by looking at it. Which functions look easier for you to work with? Yeah. Yeah, why? Yeah, exactly. And that is for starters, until you actually have some experience and can see, that is a great way to think about it. Look, in the first case, I have to work with x squared over 2. In the second case, I have to work with x and 1. Okay, it's not really a choice. I'm going to choose the simplest one. And it so happens that if you were to choose 1, you would never finish the problem. Okay, so this is kind of the drawback of the by parts, that if you choose your f prime and g prime wrong, you might end up in a loop where you actually don't solve the problem. I will write problem number 1 just for you guys to understand what I mean by a loop, because there are going to be problems where you are going to have this nasty choice, and it's better to recognize when you should stop and start again rather than just continue and hoping it's going to work. So let's say I haven't noticed that change. Okay, Let's say I haven't noticed that 2 is much easier to work with. So I'm gonna work with 1. I'm gonna write the formula again. Hopefully you guys remember it after you're done today. Is equal to f of x, g of x. Okay, so this is the formula. Now I'm just gonna use case 1 and replace into it. Okay, so for case 1, it will look like this. Integral of x e6x dx plus what's f of x is just x squared over 2 times g prime, that's 6 e6x dx, is equal to f of x, which is x squared over 2 times g of x, which is e6x. Everyone okay with what I replaced? I basically just took the functions from 1 and I plugged them in. I didn't do anything. Now, after you first do the by parts, it's good to spend a second and see, am I getting closer to solving it, or is it getting worse? So let's take stock of where we are. This, I need to find out. This is done. There's nothing to do here. Now, the problem is that I don't need to compute this anymore, but I need to compute this. I need to compute. And now you should look and see that this one is actually worse than what I started with, because I have x squared here, here I had x. So the formula that I have to compute is actually getting worse if I choose this by parts. Okay, right? This is what I had to compute originally, x times e to the power of 6x. Now I have to compute x squared times e to the power of 6x. So it just got worse. Okay, it got worse. So since it got worse, I should think right now, okay, maybe this by parts, this case 1 is not good. This maybe not what I should be doing. Okay, because what I'm telling you guys is, if you continue doing this, you're not going to solve this. You're not going to be able to tell me in the end what the solution to this is. Did everyone understand the logic why this is bad? Why I should stop right now when you see something like that? Right, so we're gonna start again with the process and see where we're at. So I've been giving you to compute this thing, and this is a standard. It looks standard, like something by parts. So you start identifying what f of x and g of x are, and then obviously you have two cases. You either identify the first one as derivative or the second one as derivative. And now let's say that you haven't noticed that the second one is going to be much easier. So you just say, okay, let's try the first one. And I plug in the first one. And I get this thing. Now, the problem is that if I move this thing on the other side, my integral of x e6x dx is equal to x squared over 2 times e6x minus integral, just put a 3 in front so it looks obvious. This is me basically just moving the thing on the other side. At this point, I should notice that I started here, I needed to compute this, and now I have to compute this. The difference is that now it's even worse because I moved from 1 to 2. So the formula actually got worse to compute. And at this point, I should be like, I'm stopping right here and I'm going back to my by parts thing because something went terribly wrong. Okay? If after the by parts you see something that's uglier than what you started with, you should stop and see if maybe there isn't a better by parts. Okay? So this, I would just stop, like literally stop right now. Stop. And now let's see. If I try the second method, if I substitute with the second idea, who someone from the public claimed it's easier, what do I get? Is it actually easier, or is it actually bad? Now, so I'm gonna write the formula again, just so we have it here. Okay, let's do the second replace. Let me see. Let's do with the second replacement. So, okay. So f prime of x is 1. So I have 1 times g of x, which is e6x over 6 dx, plus integral of f of x, which is x times g prime of x e6x dx, is equal to x times e6x over 6. Okay, I'll raise it right now. So I basically just replaced with the new values. And now let's take stock of where we are. This is what I wanted to compute. This is what I wanted. This is done. So I only have left this left. This is left. And now you should be like, oh, I'm actually doing something good, because this looks much nicer than this, because there's no x, right? I have 1 in front. This is just integral of an exponential, which we've solved last time multiple times. So right now I can just write the solution. Integral of x e6x dx is equal to x times e6x over 6 minus integral of e6x over 6 dx. And the whole point is that you can solve this one. You know what that one is. That's just an exponential. So my final answer is just x times e6x over 6 minus 1 over 6 times e6x over 6 plus a constant. Okay, now, any questions on what I did? On my choice of replacement, on anything? Okay, now let me ask you some different questions. What if, for example, I had to compute the definite integral? What if I had to compute integral of, I'm going to copy the same thing, integral from 0 to 1 of x e6x dx. So basically the same integral, but from 0 to 1. How would I solve this? The answer is I would solve it exactly the same. Exactly the same. The only difference would be that I would just carry the numbers from 0 to 1 everywhere. So I would solve it exactly the same. Nothing changed, except for I would write integral from 0 to 1 of 1 times e. I'm just copying from the other part, from the other page, plus integral 0 to 1 x e(x) dx is equal to x times e6x over 6 from 0 to 1. So the by parts works even if it's definite, even if it's indefinite integral. It doesn't matter. Okay, it works exactly the same. So just to give you a final answer, my integral would be 0x ex dx is equal to, I'll plug in the numbers here, 1 times e to 6 over 6 minus 0 times e 6 times 0 over 6 minus, what was the other integral? 1 over 6 times e6x over 6 from 0 to 1. Okay. Which I'm just going to replace again. E to the power of 6 over 6 minus, what is this? Oh, I hate replacing. E6 36 minus E0 36. And this is a number, I would just leave it like this, I wouldn't bother. Okay. So basically, all that I wanted to show you is you can use by parts in a definite integral exactly the same, solving it exactly the same. Just put 0 to 1 in the end. Now for the actual harder question. What if I had integral of x squared e6x dx? What if I had x squared there? It's possible I get that problem solved. How would I deal with it? Any ideas? Well, it still looks like one of the cases that I mentioned in the start, right? It still looks like one of these cases over here. It still looks like one of those. But if you followed a little bit, then you're gonna be like, yeah, but we basically got to the same integral right here, and you said I need to stop. So how does that make sense? And what I'm gonna say to that is the reason I stopped here when I had to compute the same integral is because it was worse than what I started with. It was uglier than what I started with. I did not say it's impossible to compute. I just said it's impossible to compute if you're going to do it this way. Okay. So my thing still stays. If you after you use the by parts, if you get to something that looks uglier than what you started with, you stop and you try the other way. So let's see what I do in this case. Unsurprisingly, I'm going to use the by parts again. And again, two cases. F of x is equal to x squared. G prime of x is equal to E6x. So F prime of x, let's keep standard to what we're doing up to this point. The first one was F prime, and the second one was G of x. That was the first term we used. So F of x in this case is x the third over 3, and then G prime of x is 6E6x. That's the first case. And then the second case is F of x is equal to x squared. So F prime of x is equal to 2x. G prime of x is equal to E6x. So G of x is equal to E6x over 6. Okay. And now, again, the same argument comes. Before, when you're choosing which one to use, which one looks simpler? Again, I have x to the power of 2 here, x to the power of 3. If I look down below, I have x to the power of 2 and 2x. So there should be no doubt that I'm gonna choose 2 again, right? It just looks easier to work with. But let's, again, for the sake of it, let's write both of them and see what I mean. If I were to do case one, I would have, let's write the formula again since I'm f prime of x, g of x, d of x plus is equal to f of x, g of x. Now, in the first case, my f prime is x squared times e6x dx plus integral f of x is x to the power 3 over 3 times g prime 6e6x dx is equal to f of x 3 times g of x e6x. Okay, so this is the first one. I already should be kind of noticing that it's getting worse. I'm moving from power 2 to power 3. That's never a good sign. It means that if I keep on going, I'm going to get to power 4 and so on. But if I do it in the second case, I get integral of f prime 2x times g of x, that's e6x over 6, d of x plus integral of x squared e6x dx is equal to x squared times e6x over 6. Okay? These are the two cases. These are the formulas in the two cases. Now, again, it's good to take stock of where we are. The right-hand side is done every time. This is done in both cases. So I don't need to worry. There's no complication that's going to come to me from what's on the right-hand side. There's nothing to do with it. That's already part of the solution. So right now, I have this. This cubes is what I started with. And depending on which case I'm in, I wish I had a color. Oops, sorry for that. Oh, found blue. Well, in each of the other cases, I have to compute what's in blue. If I'm in case one, I have to compute that thing. If I'm in case two, I guess the color doesn't really work on this. If I'm in case one, I need to compute the blue thing or the curly thing. And if I'm in case two, I need to compute this one. Now, I'm asking you from a, yeah.
I'm just wondering if this is a general thing about the integration parts that you don't need to care about the right-hand side.
Yeah, you don't need to care about the right-hand side because there's no integral sign on the right-hand side. So if I had it definite, I would just replace the numbers. If I had it indefinite like this, I just leave it there. It doesn't affect anything. But moving on, if I'm in case one, I need to compute this, and if I'm in case two, I need to compute this. And now it's good to just try to develop the sense, looking at it, which seems easier for you guys to compute. Is the x to the third easier to compute, or is the x easier to compute? And at this point, you should be like, I'm definitely not going to do the first one. It's just higher power. Why would I want the higher power? I'm always going to do the easier one, which is this one. Okay? So this is when I make the decision. In this, unless you want to purely memorize the standard that, which f prime you take, etc., you're always free, especially on the scrap paper, to just write both cases and see which one is worse or which one is better. Okay? But usually when you're going from a smaller power to a bigger power, it's a bad sign. When you're going from a bigger power to a smaller power, it's a good sign. So I don't know how to write, but if you're going from big to small, this is good. If you're going from small to big, this is bad. I don't know how else to phrase it nicely. Okay? But basically at this point, I'm going to solve problem number one. Oh, problem number two, sorry about that. I'm going to disregard problem one. So I'm just stuck with solving problem number one, which I'm just going to rewrite. Integral x squared e6x dx is equal to x squared times e6x over 6 minus integral, let's move in front, 1/3 x e6x dx. Okay. Now, hopefully, the last integral that I have to compute, specifically this one, looks familiar to you guys because we just solved it 2 seconds ago. And how did we solve it? We applied by parts to it, right? So this, I wanted to show this example to basically answer the questions. Can you use by parts multiple times? Yes, you can use it as many times as you want. Okay? So right now, if I were to solve this problem to the end, I would just take this fraction out, take this fraction, this integral out, apply by parts to it, solve it, and then plug it back in. Okay? Luckily for me, I solved it already somewhere here. Yes, luckily for me, I solved it already here using the by parts. So I will just take this and plug it there. If you want the full answer, it's just minus 1/3 of everything that's here. And I'm just gonna copy it, although you don't have to, because I'm not really showing any intuition here. Okay, this would be the formula. But again, the only thing I wanted to show here is that you can apply by parts multiple times. It works. And as long as you are dropping your power, as long as you're going for a big power to small power at every step of your by parts, then you're doing something right. If you're going up in power, so for example, if I were to choose problem number 1 and I would apply by parts, I would eventually just get x to the power of 4th, 5th, 6th, whatever. So at that point, it should be clear that you're never going to solve the problem and you need to change the approach. Okay. I think this is a great time for a break. We should just take like a 10-minute break, and then we'll see if we'll do more examples or move to the substitution part. All right, guys. So let's get back to it. So I think we've gone through most of the examples that I've planned. Realistically, everything that I would do on by parts right now, I would basically just repeat the exact same process for everything. And I do think it's at this point pretty telegraphed. But before we move on, are there any questions on what I did? Anything, any particular part that you would like me to go over again or something like that? Because what I can guarantee you is you will use by parts. I'm pretty sure even on the exam under some shape or form. So it's quite important that you get what I did here. Okay. So anything here, or is it clear to everyone basically what I did? Okay. I'm gonna, since there's no questions, I'm gonna assume everything is fine. Now we're just gonna move to substitution, which is the last part of the big like method to solve integrals, and in my opinion is the highest skill expression method that we're gonna find, right? So the reason is in the by parts thing, I gave you like some cases right here, in which case if you see them, you should expect to use by parts. Substitution, it's not that clear cut. You can basically solve, I would say, almost any problem that you're gonna face with substitution, and sometimes way shorter than I would solve it. It's just the question is, can you see it? Can you see things that I didn't see or not? And let me explain exactly how it is. Substitution basically comes from the idea of the chain rule derivation, okay? How did we have the chain rule derivation? It was, so first of all, let's do it. Substitution, Substitution. And I'm only gonna do the indefinite integral today. Okay. It all comes down from the chain rule. What's the chain rule? If I had something derivative with respect of what was it? F of g of x, derivative of x. What was this? It was f prime g of x, g prime of x. Okay. Now, I'm not gonna show you the whole, I'm gonna apply the integral thing because I need to make some arguments and it's gotta get more complicated. But I'm gonna draw the final answer in which if, for example, I'm supposed to compute f of x d of x, right? I'm supposed to compute this integral and I have no idea how to do it. I tried by parts, it didn't work out. It's not a simple function, so what am I supposed to do? The idea is that I can just write, instead of this x, I'll just write u of x. I'll just put a u here instead. I'll just replace x with u of x. And I'll write it something like, I'll say this is equal to integral of f of u, which is of x in parentheses like this, times u prime of x dx. Okay, and now for the final touch is I'm just gonna say this is the actually integral f of u, and instead of this, I'll write d of u. Okay, so basically I'm just changing the variable after which I'm integrating, and this method is extremely powerful. And I'll give you some examples right now where it just makes an integral which is potentially very hard to solve or unsolvable, that just makes it easy in like 2 lines. Okay, but this is the whole idea. The whole idea of substitution is I'm just substituting my variable and I'm changing what I'm taking derivative of. That's the whole idea. So let me give you an example. Let's say we have to do integral of x square root of x minus 1 d of x. This part, I think, I haven't really thought of it that much, but I think you could actually solve this by, well, maybe you could solve it by parts. Maybe. I don't think so, but maybe. I can add another factor if you think you can. I'll just make it a little bit more complicated, and I can assure you you won't solve it. Okay. So the whole idea is to look for a different method. Whenever you have square root of something that you want to get rid of, or 1 over something you want to get rid of, substitution is a great way to think about it. So how am I going to use it here? Well, what's bothering us? What makes this integral very hard to compute? It's the square root of x minus 1, right? If it was square root of x there, I could solve it. It would make my life very easy. So what I'm going to say is like, okay, x minus 1 is equal to u. Okay. Now, I'm going to take derivative, and I'll have dx times derivative of x minus 1 over dx is equal to du. Oh. Yeah. And this is just going to be dx times 1 is equal to du. So the steps of substitution are: you first claim your substitution in the indefinite. You claim your substitution. So I claim that is my substitution. And I can't, as I said, substitution is like very high skill method, right? You can do a lot of cool things with it. So I can't tell you use it then, because you might find even better uses for it than me. But sticking to the basics, I claim my substitution. I then express dx in terms of du, and after that, I replace and change my new integral. So let's change it together, okay? So what does this equal? This is equal to, instead of x, what should I write? Instead of, so if x minus 1 is equal to u, then x is equal to u plus 1. So instead of x, I'll write with black, I'll write the final answer, and with blue, I'll write the equivalent of what it was before. So this is u plus 1, which is just, I'm just replaced my x. Then I have square root of u minus x minus 1 is just u, which was x minus 1. And now dx. So I know it's, so in case you're going to tell me it's wrong, once you do the change of variables, you can't have x and u under the same integral anymore. You either have only x or you have only u, okay? You can't integrate, for example, bananas over apples. It just doesn't work that way. So when you do the change of variables, you commit to this change, and in the new integral, I'm only going to have u. So this dx is wrong, very wrong. It's times du. So again, the steps of what I did here was, I first identified that I can't solve this problem. I just can't. So I'm just going to choose my change of variables. X minus 1 is equal to u. Just because usually square root of a formula is really ugly. So that was my idea. I claimed my change. Then I just expressed dx in terms of du, like this. And then I replaced everything in my new integrals. Instead of x, I wrote u plus 1 for my change. Instead of x minus 1, I wrote u. And in my case, dx is equal to du, so I just plug them in, and I'm safe. Okay? Now, why did I do all of this? Well, the reason is that this integral that I have to compute, integral of u plus 1 square root of u du, is a very nice integral, right? It's a polynomial integral. It just works out nice. Because if I distribute this square root of u, I get integral of u square root of u du plus integral square root of u du. And we have formulas for this, right? I showed you formulas last time, because this is just integral of u to the power of 3 over 2 du plus integral of u a half du. This is just equal to u 5 over 2 over 5 over 2 plus u of 3 over 2 plus a constant. In case you're confused what formula I used, integral of x to the power of a dx is equal to x to the a plus 1 over a plus 1 plus a constant. In case you're wondering what formula I used. I wrote it last time, pretty sure. Now, am I done? That's the question. Am I done with this problem? And the answer is almost. I started here. And I ended up here. So my answer is integral x square root of x minus 1 dx is equal to u 5 over 2, whatever this is. I should have made nicer numbers. Anyway, I get to this point. And remember, apples cannot be equal to bananas, okay? So I need to change my u back to dx in order to give the final answer. So I know that I know that u is equal to x minus 1, so I'm just going to replace everything up. X minus 1, 5 over 2, 5 over 2, plus x minus 1, 3 over 2, 3 over 2, plus a c. Okay, now I'm done. So, this is, in the end, this is realistically maybe a 1 out of 10 mistake, but it's 1 point that you're basically losing because you were lazy and didn't replace some numbers. So don't forget this, especially because if the problem would go on and you would use this solution, you would be quite very wrong and you probably lose everything in the next problem. So always when we're doing substitution, substitute back when you're trying to give the final answer. But any questions on this? Any questions on how I substituted things? We have some other examples which I'm gonna do. Maybe you guys get questions then. But it's a very, very strong method. I would highly advise you not to sleep on it. So let's take this one. Let me think actually. Okay. Integral t to the power of 3 over 1 plus t squared d of t. This is what I want to compute. Can it work through by parts? I really don't think so. So what am I thinking of? What's going through my head? And outside of panic, I should be something like, okay, what's making this ugly? What's complicating this? Why is it not an easy function for me? And the reason is this 1 plus t squared. If I had there t to the 10, it would be very easy, right? In my head. So in my head, I'm just thinking something like, okay, if I had t to the power of 3, t to the power of 10, this is t to the minus 7. I know how to solve this. I have a formula. Everything is nice. So this is the problem, that 1 minus t squared. So what do you do with your problems? You just postpone them. Well, in math, usually we just replace it, right? So I'm just going to say, okay, u is equal to 1 plus t squared. And that's why I'm saying that this method is quite limitless, because you can, any integral you see, if you think you have a smart substitution, just go for it. Okay? It doesn't matter if that's not how the problem was intended to be solved. If you have a smart substitution that just solves a problem in 2 lines, congratulations, you saved like an hour of work. Anyway, so I said the first step is I claim my substitution. The next step is just to see what du is in terms of dt. So I take a derivative. Du is equal to 1 plus t squared, derivative with respect to t, times dt. Okay? Now I just write it out. Du is equal to, what's this derivative? It's just 2t times dt. Okay, now I've claimed my substitution. I've written du in terms of dt. Let's just try to substitute into our function. So my function is integral of t to the power of 3, 1 plus t squared dt is equal to integral of t to the power of 3, 1 plus t squared. Instead of this, oh, sorry, I forgot to replace. 1 plus t squared is just u, and I have dt. So this is a big problem that you're all going to face at some point, right? At this point, if I just try to replace, the substitution is not as easy as it was in the previous case, right? Why? Well, first of all, I can't just replace this dt with du, because dt is not equal to du. Du is equal to this thing. Okay? Second, I have t to the third here. I only know about t to the second. So at this point, I'm kind of like, this is looking very bad. Okay. So you need to think a little bit and see exactly, can I do something? Can I force some change? I don't know. So here's my idea. I have integral of u. This u is the only thing that looks nice. Everything else looks terrible. But let's see. Can I do something to this t to the third? My first idea is, let's just write it as t to the power of 2 times t. Everyone on board with that? So I'm just going to write it like that. So I'm just going to say t squared times t times dt. And now let's see, am I seeing something here that I can use? Well, let's see. T dt is the same thing as t dt from here. So I'm just saying, instead of t dt, can I just write this as du over 2? So again, I claim my substitution, I did the math, and I got du is equal to this formula of dt. And now when I try to replace into my formula, I noticed that it's not as obvious as I would have liked it to. So I need to do something to it. And after thinking for 5 minutes and not panicking, I realized, okay, let's just split t to the power of 3 into t squared times t. Okay? So I have t squared times t here. And the reason I chose to do it this way is because now I can take advantage of this t times d of t. Okay? T times d of t is equal to du over 2 from here. All right? So now I can just write this as integral of t squared times du over u. Oh, du over 2. Sorry about that. Okay? This is looking much better. Am I done? Not yet. I need to substitute, get rid of the t squared. Is it good? Is it bad? Well, luckily for me, I know that u is equal to 1 plus t squared. That was my substitution to start with. If this is my substitution to start with, then t squared is just u minus 1. So finally, my final answer is just integral u minus 1 over u times du over 2. This half goes in front or whatever, and my final answer is just half of u minus 1 over u du. And this looks much better than the previous one. And from here, I have no doubt that you would actually manage to solve this quite easily. But I would rather just go through the substitution again, because that's basically the tricky part. So when I looked at this function, my first thought was that this 1 plus t squared here makes things unnecessarily difficult for me. So I said, okay, let's just get rid of it. So I replace it with u. My choice is u is equal to 1 plus t squared. After I make the choice, the next step is always to express my new du in terms of dt. And for that, I just take a derivative of this u with respect to t. After computation, I get this final answer. Du is equal to 2 times t times d of t. That is my final answer for du. And now once I got this, I can already try to replace some things inside. And I go in and I replace the things. This is a more complicated example because the only thing I can replace immediately is this 1 plus t squared. I know this is u, so I just write u. Okay? The rest of the function, which is t to the power of 3 and d of t, is more complicated. I still need to get rid of them. Remember, when I commit to a substitution, I either have only t's or only u's. So in this case, having t and u and d of t is very wrong. I'm basically just writing this in multiple steps so you see what I'm doing. But when you replace, especially in writing and in an exam, you write the replacement all at once. You show me the steps in T, but you write the replacement all at once. Just because it forms a good habit. So I'm stuck here. This is going in my head, and I'm stuck here or on the scrap paper. And I don't know exactly how to get rid of t to the power of 3 and dt. I just don't know. But then I'm thinking, okay, in order to get rid of this d of t, I need a t, right? I need t to be multiplied by d of t. So the way I do that is I just split my t to the power of 3 to t squared times t. I just split it like that. Because I want to create this term right here, t times d of t. I'm creating this term right here. And I know that this is equal to du over 2 from my original formula right here. So I plug in that, and now I'm stuck with this t squared. But luckily for me, this t squared is just equal to u minus 1, just because u is equal to 1 plus t squared. It's just from a replacement. And now I'm stuck, and now I got to this final nice integral to compute. Any questions on what I did to the substitution? Or was it clear how I thought about it, how I tried to do it? Now, as you can see, you need to work in a specific manner. So that's why I said that it's a little bit of a skill expression and it's a little bit harder, is because not every substitution that you will choose will work out. For example, this problem was made to be solved like this, because if for example, I just had a different power here, I had t to the 4th, for example, then there's a chance this substitution wouldn't have worked. Okay? So that's why when you're trying to solve a problem through substitution, you actually got to work out the math. There's no way, unless you have a huge experience with integrals, in which you're going to tell me by looking at the integral, this is not going to work or this is going to work. Okay? I don't believe you unless you actually show me that the replacement worked. Because again, if I put t to the 4th here, this replacement doesn't work. It's bad. Okay? But, it would work, luckily for me. So now I'm just stuck to solve this integral. Which is it's quite nice, because this is equal to a half of u, okay, u over a u minus 1 over u d of u. I just split it into 2. And this is equal to a half of integral, what's u over u? Is just 1 du minus integral 1 over u du. And what are these integrals? This is just a half of, this is u, minus, this is ln of u, plus a constant. And now just to be done, I am just gonna replace u with 1 plus t squared, which was my original thing, and I get a half of 1 plus t squared minus ln 1 plus t squared plus a constant, and that is done. So this is what I'm saying, that a pretty complicated problem, if I just choose the correct substitution method, it just becomes quite easy. Okay, the hard part is just choosing the substitution and doing the substitution correctly. Other than this, let's see, do I have anything smart as an example? Oh, I guess I could do this. Okay, I think this should work. I'm not convinced. Any questions on what I did? Yeah.
Can you choose it back for you?
Sure.
Is part of the original expression or?
No. You can choose, great question. You can choose any formula you want in this world. Like realistically, if you solve this with a substitution that doesn't make any sense to me, it doesn't matter if it makes sense to me or not, as long as you solved it. So substitution works for any formula you can come up with. If for some reason you fought and you said, okay, let's substitute this with 25 plus square root of t times e to the power of t, and it worked out, I'm like, all for it. Congratulations. Okay. Do I think that's gonna work? Probably not. But if you can find something, it works perfectly fine.
But on this course, it's going to be the expression.
I would say that in this course, the chances of the problem being solved only by your amazing choice of u that's not in the expressions are somewhere below 0.5% or less. So I would say that usually when we have to use substitution, it's gonna be something in the expression. But that doesn't have to limit you guys. You can think outside the box, right? But no, usually in this course, the substituting thing will be in the expression, I would say. All right, let's try a very, very simple one, very short. It just showcases the power of this thing. Integral e square root of x dx. And since we're almost done, I'll give you 3 minutes to solve it. Then I'll solve it, and then we're gonna end it here. In case you're wondering, yes, the substitution is in the formula. Just for the hint, the substitution is in the formula. I'm not asking you to do any crazy substitution. All right. So first of all, I think this problem is basically encompasses everything that you've learned in terms of substitution and by parts, as I'm going to show you. So if you got somewhere on the road or something, you should be very proud of yourself with basically 1 hour of experience in integrals. Otherwise, it's perfectly normal. But this problem just shows how simple, like you can't get a much simpler formula than this, right? How a simple formula can get very complicated. And I think in math, you should usually be scared when you see a very simple formula, not when you see a complicated one, especially in this course. Most of the formulas you're gonna get are gonna be very ugly, but they solve, I would say, easier than this, which is like as short as it can be. But coming back to actually solving it, I said the substitution is in the formula, so I would assume you guys got it. It's u squared root of x. So good job if you got it. Honestly, there were not many options to start with. But still very good stuff knowing that you've learned substitution for the last 10 minutes. Now, what's the next step? We just get du in terms of dx. So I have derivative square root of x over dx times dx. Okay? Now, this is where it becomes kind of ugly. Du is equal to, what's this derivative? Is just, hopefully I'm not losing my head, but it's just a half times 1 over square root of x. Please tell me I didn't mess this up, but it seems fine to me. Okay? Now, let's attempt to replace it, which I assume is where most of you got stuck. So when I replace this, I get integral e, instead of square root of x, I can write u, which makes it very nice. But then I have d of x. So I'm kind of mad. I'm stuck here. Okay? So I'm stuck, and I'm thinking. And the trick is here. What's the trick there? What is square root of x? It's just u. Okay? So do you guys agree that I can just write this d of u is equal to a half times 1 over u dx? Because again, square root of x is equal to u, so I just replace this. Everyone okay with that? So now I can just write, I move u and 2 to the other side, and I say that 2 times u d of u is equal to d of x. So again, I just moved this u and 2 to the other side. And I get 2 times u is equal to du, 2 times u times d of u is equal to d of x. Everyone okay with this? Cool. Now, my last step is I'm just going to replace this d of x here with this d of x. And I'm going to get integral e to the power of u times, what's d of x? It's 2 times u times d of u. And is this a good substitution? Yes, because now I have everything in terms of u. So the substitution worked. And now, if I just put the 2 in front because it's a constant, does this look familiar to any of you? Hopefully. Does this integral look familiar to any of you? It's just the by parts example we did in an hour ago. Right? I think ours was 6x or something like that. See, it's right here. It's just by parts applied to it. And just because we have 5 minutes and I'd like to finish this, how would I solve this by parts? Is just I write my two cases. F prime of u is equal to E of u, so F of u is equal to E to the power of u. G of u is equal to u, so G prime of u is equal to 1. Or the other case where I have F prime of u is equal to E of u, so F of u is equal to E of u. G prime of u is equal to u, so G of u is equal to u squared over 2. Right, remember these two cases that we wrote? Now the argument is that I'm not gonna write again all both cases and whatnot. I hope you can see that E of that F is basically the same everywhere because it's exponential. And then I'm gonna choose the simplest one, which is case number 1. Right, it just has simpler powers. So just to give the final answer, this is equal to, well, let's write it. So the formula was F prime x g of x dx plus F of x g prime of x dx is equal to fx g of x. If I just plug in the first case, I get integral EU to the power of u dx plus integral e to the u, du, sorry about that, I don't know what I'm smoking, du is equal to e to the power of u times u. Okay, so you basically just have this, I plugged in the values, and now I can just take this one out. That is just equal to just keep this in mind. I'm keeping this 2 in my head. 2 times EU times u minus integral EU du. And just to finish everything up, 2 EU times u minus E of u plus a constant. And u is equal to square root of x. Again, really important that I replace 2 e square root of x times square root of x minus e square root of x. And the constant. Yeah, this is so this simple example basically combined everything that we learned today, which was the substitution, and which allowed us to get to the by parts and finish the problem up. But the whole trick here with the substitution was that I could just straightforward replace d of x with things that only depend on u. That was the trick here. That d of x was equal to stuff that only depends on u, so I could just plug it in, and I got this by parts looking thing. But yeah, this was all for today. If you have any questions, otherwise, you're free to go.